Hello and welcome. My name is Jason Koenig, and I'm here to talk about first-order quantified separators. You may be familiar with a linear separator, which for a set of points in the plane labeled positive and negative is a line that separates them. In this work, we're not going to consider linear expressions, but rather quantified formula as separators. We're interested in these formula because we want to infer invariance with quantifier alternation. That is, like this example from our benchmark, formulas that have both exists and for all in the same formula. Now, the contributions of this work are the identification of quantified separation as an interesting and natural problem, a practical separation algorithm, a MP completeness result, and an implementation of IC3 PDR that uses separation to infer invariance with quantifier alternation. We're going to start by defining quantified separation, and in order to do that, we need to define what it is that we're going to separate. For us, this will be logical structures, which are a way of formally representing objects. For example, if we have an undirected graph, we can represent this in structure form by defining the elements to be the vertices of the graph, and then an interpretation for an edge relation E, which models the edges of the graph. In general, a structure can also have interpretations for constants and function symbols as well. Now let's let S be the structure for this graph. Then we can say that S satisfies the formula for all x there exists a y such that E of x, y, because for every vertex it's connected to some other vertex. In contrast, we can say that S doesn't satisfy this formula, which says that every edge has a third point that is connected in a triangle. With this in mind, we can define a separator itself, which for finite sets of structures S plus and S minus is a formula P that satisfies all of the positive structures and doesn't satisfy any of the negative ones. For example, this every edge is part of a triangle formula is a separator for this set of graphs. Now there's a small issue with this definition in that if we allow arbitrary formula, we can separate any disjoint sets. In particular, we can write down a formula which is true for exactly one structure. And then if we take the disjunction of all of these formulas for all of the positive structures, we'll get a separator. Now the problem is that this separator is highly overfit to the exact examples that it was given, and so we don't expect it to generalize well for new examples. We can fix this by considering those separators as those that can be expressed with at most k quantifiers in premix normal form. This is the form where all of the quantifiers are lifted to the front of the formula and form something called a prefix. And this leaves behind a quantifier-free body, which we call the matrix, and usually label phi. So now that we've defined separation, we can present a separation algorithm. In order to do so, we're going to review what it takes just to verify if a formula is a separator. And this is very elementary, but we want to review it because it will come up when we're defining the algorithm. So if we have a separator, say for all x exists y, E of x, y, and a structure we want to evaluate it on, we start by looking at for all x, and that means we have to assign x to every value of the structure. And then exists y, and similarly we have to assign y to every value. And now at a particular point, we want to look at what the value of the matrix phi is and compute its value. So we're going to do this in a slightly roundabout way. So we're given a matrix phi, we want to first compute all of the atomic formula that are valid with the variables that we have. And we're going to map those to truth values. Then what we can do is substitute those atomic formula into phi in order to compute its value. Now, this mapping between all of the atomic formula can be computed from a combination of the assignment and the structure we're in, just by substituting the assignment into the structure. Now this mapping here in the middle is a representation of something we call the quantifier-free type, or QF type. And the key idea here is that the value of phi is going to be a function just of the QF type. So the same, if we have different assignments and structures that result in the same QF type, the value of phi has to be the same, regardless of which structures or assignments we started with. As an example of concrete QF types, let's look at what they are for this example of simple undirected graphs with two variables. In this case, we have three QF types. One where x is equal to y, one where x is not equal to y, but there's not an edge between them, and one where x is not equal to y and there is an edge between them. And because these graphs are simple and undirected, these are the only QF types that can appear. So now we can complete our verification. If we have a particular assignment in a particular structure, we can compute a QF type. And then from the QF type, we can compute a truth value for phi. And now we can label the node with that truth value, and then repeat this for all of the other nodes. And now we can propagate back up the tree using the fact that exists is equivalent to or, and for all is equivalent to and. Now all we have to do is check the label at the root is the expected polarity. And of course we need to do this for all of the other all the other structures as well. Now let's for a moment assume that we're given the prefix for all exists, but we don't know what phi is. So we're going to use this key assumption from earlier, which was that the value of phi depends on the QF type. And that means what we can do is introduce some propositional variables, a, b, and c, to represent the value of phi on each distinct QF type. Now, as before, we can label the leaves with these variables. And now when we go back up the tree, we're going to combine things symbolically. This results in a structure formula. Now, in order to actually find a separator, we can build a SAT query by assigning the value of each structure formula to the expected polarity. And then this conjunction will be satisfiable if and only if the structures are separable. And we note that it's possible to construct an explicit syntactic separator given just a SAT assignment. Now this is all for a fixed prefix. To get a full separation algorithm, we can just test each of the prefixes in turn. So in practice, the algorithm we use differs from this naive version in a couple ways. So we gain some performance by expanding the tree lazily. Also, instead of allowing any possible matrix, we limit the number of clauses the matrix can have when expressed in CNF form. This allows us to trade off both matrix complexity and quantifier complexity. In particular, we explore the number of quantifiers and the number of clauses in a diagonal fashion, and this ensures that we find the simplest separator in some sense, where that sense is the minimal number of the sum of these two parameters. We also support one further extension, which is to add implication constraints. These are a pair of structures such that if the separator is true for the first structure, it must be true for the second. So of all of the four ways that an implication constraint can interact with the separator, only one of them is disallowed. These will be very useful for invariant inference. I want to take a moment to talk about the complexity of separation. In order to do that, we're going to define a family of decision problems, K-sep. And these will be the problem of determining whether some given labeled sets, S plus and minus, are separable with a pre-next normal formula with at most k quantifiers. So the algorithm that we just presented shows that separation can be reduced to SAT. And we can show the reverse as well, that SAT reduces to K-sep for any k greater than or equal to 2. Together, these are going to show that for a fixed k, K-sep is NP complete. If we let k be an input, then just verifying whether a separator is correct is already p-space complete. And I'm just going to very briefly sketch this reverse direction of the reduction here. So in the reverse direction, we're going to want to take a clause of a SAT query and turn it into a structure. So if we have A or B or C, for the prefix for all exists, we're going to turn this into a 4-element structure. And the structure is going to have this very specific pattern of QF types. And separately, we're going to ensure that phi of t must be true and phi of s must be false. This means that when we compute our structure formula going back up the tree, we get a simplification that happens such that the structure formula is equivalent to the original clause. I'll refer you to the paper for all of the details of this reduction. I'd now like to talk about invariant inference using separation. We're going to be inferring the invariants for transition systems, which consist of a set of initial states, a set of transitions between states, and a set of bad states that we want to eliminate. And all of these are going to be specified as formula in uninterpreted first-order logic. Now, an invariant for such a system is a formula I such that the initial states all satisfy I, and the I is preserved under the transition relation. In particular, if we start in a state satisfying I, then all of its successors will also satisfy I. And finally, we need I to eliminate the bad states. In order to infer invariance, we're going to adapt an existing inference algorithm called IC3PDR, and we're thus going to obtain the first system that's able to infer invariance with quantifier alternation. IC3PDR is an algorithm that finds invariance incrementally, in that it finds the invariant conjunct by conjunct. Each of these conjuncts is found using an inductive generalization query, and we're going to use separation to solve these queries. And the rest of the algorithm outside of this is entirely standard. So an inductive generalization query is we're given a state S and a formula Fi minus 1, and we want to find a new formula P that satisfies these equations. We want P to not satisfy S, we want P to be true for all initial states, and we want P to be relatively inductive to Fi minus 1. That is, whenever a state satisfies Fi minus 1 and P, all of its successors must also satisfy P. Now, in order to solve these equations, we're going to use a series of separation queries, and we're going to accumulate constraints until the separator P is a solution to these equations. Concretely, we're going to start by adding S as a negative constraint, and then we're going to ask for a separator P. We're going to pass the equation init implies P to an SMT solver, and this SMT solver is either going to say, yes, this equation is correct, or no, and give us a concrete counterexample. We can add that counterexample as a positive constraint and go back and find a new separation, a new separator. Then if the init does imply P, then we can ask the same question of the other formula. And in this case, if we get a counterexample, it will be actually a pair of states so that we can add as an implication query, or as implication constraint to our query. Then if once the answer to both of these questions is yes, we have found a solution to the equation. So this describes our invariant inference algorithm. And so now we can discuss its results on a collection of distributed protocols that have been modeled in prior work. And we have both examples with universal only invariants and those whose invariants require quantifier alternation. For the universal only ones, we can compare against universal PDR, which is another adaptation of IC3PDR. So the results on the universal only examples are mostly comparable to prior work, with a few exceptions. For examples that involve quantifier alternation, we're able to solve some of the examples from our benchmark. Most of the examples that we don't solve are Paxos or its variants. So our results from our experiments show that the SAT instances that we get from separation are actually solvable in practice. One thing that we want to note is that even though we separation itself is NP complete, actually checking whether or not the resulting separator is an invariant may not be decidable. In particular, if P has general quantifiers, then the SMT solver can't necessarily determine whether or not it is correct, and it may or may not give us a counterexample that we can use to proceed. One possible solution to this problem is to generate only separators from a decidable logic fragment. Finally, we note that the heuristic we're using to generalize is a minimal number of quantifiers and clauses together. This is a very different heuristic than the heuristic is used in other invariant inference algorithms, in particular universal PDR. We also note that this combination gives better generalization than just minimizing the number of quantifiers alone. In conclusion, we present first-order quantified separators as a primitive for invariant inference. We give a concrete algorithm, and we show that the corresponding decision problem is NP complete. We also present an adaptation of IC3 PDR that uses separation to infer invariance with quantifier alternation. And we show that this algorithm is able to infer invariance for some non-trivial distributed protocols. Thank you for your attention.